Okay, so now we're looking at implicit differentiation, which is, well, it's not really a separate differentiation rule because technically all we're going to do is apply the chain rule, but the technique is important enough to deserve its own name, to deserve its own chapter, to deserve its own place in mathematics. Let's take a look at what it does. So basically what we're interested in is taking the derivatives of really inconvenient functions. So for example, if we had this function y cubed plus 3y squared minus 4 equals x squared, well, that's really inconvenient because that's not even a function, right? That's an equation. But there are theorems that say, okay, if something is encoded in an equation like that, we can represent y as a function. And technically speaking here, we could solve this equation for y, but the formula is horrible. And there are quite a few equations that cannot be solved symbolically. And so rather than trying to find ways to solve symbolically that ultimately really don't even exist, we're going to note that in any equation, we can interpret the y as a function. And because equal functions, and basically these two sides are now equal functions of an equation, equal functions in an equation, because equal functions have the same derivatives, we can take the derivative on both sides of the equation and get a new equation. And the main challenge there is to remember that y is a function. We'll see that when we actually do the computation. But what that means is that we must use the chain rule to differentiate any terms that have y. So if y is plugged into a function h, and basically up here y is plugged into the function something cubed plus 3 times something squared minus 4, right? Then the derivative of h of y will be the derivative of h of y of x technically, so it is a chain rule because y of x is plugged into h. And by the chain rule that gives us h prime of y of x derivative of y with respect to x, which is h prime of y of x times y prime of x, and typically we ultimately drop the arguments again and just say h prime of y times y prime. Let's take a look at that in the example. So let's look at the function y that satisfies y cubed plus 3y squared minus 4 equals x squared, and we want to find its derivative at the point 0, 1. Okay, so first step, we just replace the y's with y of x's so that we remind ourselves that y really is a function. And then we take derivatives on both sides, and I just stuck d dx's in front of both sides here. Now we take the derivative. We know the derivative of y cubed is 3y squared, and here's the crucial thing. We've got to make sure that when we take derivatives of stuff that depends on y, that we also multiply with y prime, because this is a chain rule. And what does the chain rule say? You take the derivative of the outside, plug in your y, and then multiply with the y, right? Same thing then also for the derivative of 3y squared. It becomes 6y of x times y prime of x by chain rule. The derivative of negative 4 is, of course, just 0. And on the right side, 2x squared is still differentiated as before. Okay, so now this step is just dropping the arguments. Nothing happened here. It's 3y squared y prime plus 6y y prime equals 2x. And we're interested in y prime, and we can see the y primes only occur as factors, right? And that's because the chain rule will always spit them out as factors at the end of the terms. So this is something that will happen all the time. And if y prime occurs as a factor, well, then we factor y prime out. So this is y prime times 3y squared plus 6y, not y prime off. And the right side is still 2x. We divide by the 3y squared plus 6y, and we end up with 2x over 3y squared plus 6y. And if we're now interested in the derivative at 0, 1, well, we just say y prime at 0, 1. That's this expression here at x equals 0, y equals 1. And we just plug that in, and, well, 2 times 0 divided by anything that's not 0 is 0, so that all works out. And, well, certainly we can also check that graphically. Here is the graph of the equation, and here's the graph of its tangent line at 0, 1, and that all looks very much like it should. That really shows that the tangent line here is horizontal, as we predicted through differentiation. Okay, so how do we take derivatives with implicit differentiation in general? Well, in the equation we have to determine the independent variable, which is typically x. We have to determine the dependent variable, which is the function, and that's usually y. Of course, names can change, but at least in here for a while it'll be like that. And especially at the beginning, it's really a good idea to replace the y with a y of x or with an f of x. Ultimately, and in fact, as soon as possible, you want to be able to keep track of that mentally, but as soon as you tend to have little slip-ups there, go ahead and just replace it with function of x. Then we differentiate both sides of the equation, and of course we've got to remember the chain rule for terms with y. And then we solve for y prime, which, as I said, is always possible because in any terms that contain y prime, the quantity y prime is just a factor. Okay, I'm not going to fix this typo here. In any terms that oh no, that is contains. In any terms that contain, I said it differently than I read it. Okay, so the quantity y prime is just a factor. And well, here's another example. Take the find the equation of the tangent line of the graph that is defined by the equation xy cubed plus xy plus 3x equals 2 at the point 2, negative 1. And well, the dependent and independent variables, the independent variable is x, the dependent variable is y. And if we take the derivative with respect to x, well, we take our equation, we take derivatives on both sides, and so here for the first term, we have to use the product rule now too, right? So derivative of the first, 1 times the second, y cubed, plus first, x, times derivative of the second, derivative of y cubed is 3y squared, and y was a function, so we use the chain rule. The derivative is actually 3y squared times y prime. Plus, well, what's the next one? The next one also goes with the chain rule, and this is one that I've seen in classes students often forget because it's just too tempting, right? The derivative of x times y is y, yeah, sure, but that's only part of it because we have to use the product rule. Derivative of the first, 1 times the second, y, plus the first, x, times the derivative of the second, which is still y prime, right? The derivative of 3x is still 3, the derivative of 2 is of course 0, and now we solve for y prime, so here is what we had on the previous panel. And we bring the stuff that doesn't have a y prime over to the right, so that's the negative y cubed, y, and 3. And we factor out the y prime, which gives us 3y squared x, or 3xy squared plus x times y prime. We divide by that to end up with negative y cubed plus y plus 3 divided by 3xy squared plus x. And if we're now interested in y prime at 2, negative 1, which is the slope of the tangent line at that point, well, that would be negative this term at x equals 2 and y equals negative 1. Let's see, if y is equal to negative 1, then the numerator will end up being negative 1 plus negative 1 plus 3, that's 1. And the denominator will be 6 plus 2, that's 8. So that should be negative 1/8. And here it's plugged in, and there's negative 1/8. All right, I can still do mental arithmetic. And the equation of the tangent line, well, the tangent line goes through the point 2, negative 1, and it has slope negative 1/8. So we set up a line that has slope negative 1/8, and at 2 has value negative 1. And, well, then we simplify, and we get negative 1/8 x minus 3/4. Sure, that's because we have negative 1 plus 2/8 here. And, yeah, so that's that one, and now we can also, again, check graphically. Here's the graph of the equation. Here's the tangent line that we computed, and the tangent line really is tangential at the point 2, negative 1. So again, we're good. Something else that we're going to have a separate presentation on is the idea of related rates. Forget the terminology, let's just look at what this stuff does. Take a look at this. Gravel is dumped off a conveyor belt and forms a right circular cone whose sides rise at a 45-degree angle. And if 2 cubic meters of gravel are dumped onto the cone every second, we want to know how fast the height of the cone increases when the cone is 10 meters tall. That sounds like one of those problems where it doesn't seem we have enough information, but we actually do. Let's first take a look at what a cone looks like. Here it is, right? And then here would be the radius, and here would be the height. And so the volume of a right circular cone, that's one of those formulas that I always prefer to piece together. Volume of any kind of pyramid in a right circular cone is a special case of a pyramid. It's a pyramid with a circular base. Volume of a pyramid always has a factor 1/3. And then it's base times height. Well, the base is pi r squared, and the height is h. The sides rise at a 45-degree angle, which means that the radius is the same as the height, right? So that gives us that. So that means that the volume of this cone in terms of the height is v of h equals 1/3 pi h cubed. And if we've got v equals 1/3 pi h cubed, we can take the derivative with respect to time on both sides because we're interested in change over time, right? And so that gives us v prime equals 1/3 pi r pi h squared h prime. I need to fix something here. All right, and we're back. Well, you've already seen it just as I did, thankfully. The derivative of h cubed is 3h squared. That doesn't change just because we're doing implicit differentiation. H prime is still on there, but I needed that 3 and I needed to fix the slides a little bit. Well, let's keep going. So once we cancel that 3, which should have had an equal sign there, hang on. And there's the equal sign. Sorry about that. I think the rest ought to work. So we cancel the 3's, which means that v prime is pi h squared h prime, which means h prime is v prime over pi h squared, all right. And at a height of 10 meters, we just plug in the data that we have into v prime over pi h squared at h equals 10 meters. So that would be v prime is 2 cubic meters per second divided by pi times 10 meters squared. That would be 1/50 pi meters per second, which is the right unit, which is the first good sanity check that we ought to be right. And if you work that out, that's approximately 6.4 millimeters per second. And well, that just shows you how large cubic units are, right? We've got this huge pile, and so even though 2 cubic meters of gravel per second is pretty huge, the height doesn't really grow very fast anymore because that gravel, of course, distributes over the whole surface of that cone. All right, well, that's that one. Last example for this presentation, I want us to find the derivative of f of x equals the tangent inverse of x. And that looks like something where, hey, you need to have a formula, right? And yet we exactly don't have a formula. And trying to use difference quotients on that thing, I would not recommend it. It feels rather painful as far as I can see. So what can we do? Well, we can look at the equation y equals arctangent of x, and we can realize that that's the same as tangent of y equals x. And for the tangent, we know the derivative, and we can do implicit differentiation. So we take derivatives on both sides again. We take the derivative of the tangent, which is 1 over cosine squared of y, times the derivative of y, which is y prime, and that's equal to the derivative of x, which is 1. Well, that means that y prime is equal to cosine squared of y, and in implicit differentiation, that would be enough. But if we have a function in terms of x, we'd like to have its derivative also in terms of x. So let's move on a little bit here. Cosine squared of y is the same as cosine squared of arctangent of y, so now we just have to somehow turn the cosine into a tangent. Well, cosine squared of anything is equal to cosine squared of that same thing divided by 1, and I've switched back to y just so I didn't have to carry through the arctangent so much. And if I now have a cosine squared in the numerator, that is the same as if I divide the denominator by cosine squared, right? So this is 1 over cosine squared y plus sine squared y divided by cosine squared y. And that's 1 over 1 plus tangent squared y, and well, that now of course gives us that it is 1 over 1 plus tangent squared of arctangent of x, and so the derivative is 1 over 1 plus x squared. Alright, so that means trig is rearing its ugly or pretty head again. In the next section we're going to take a look at the derivatives of very frequently used inverse functions, and certainly those derivatives are formulas that we ought to memorize just to be effective. But the key to deriving the derivative formula for any inverse function, as long as we know the derivative of the original function, is exactly the process that we've looked at here. Okay, I'll see you, well, for me in a couple of minutes. If you want to take a break, I wouldn't blame you. All right, I'll see you then.